Welcome to the Types of Chemical Reactions video. By the end of this video, you should be able to define the three types of reactions listed here: acid-base, precipitation, and oxidation-reduction, or redox. And you should be able to classify a chemical reaction as one of those three types. Let's start with precipitation reactions, which we've already looked at a bit. In a precipitation reaction, this is a reaction where ions in aqueous solution combine to form an insoluble or sometimes slightly soluble product. In order to determine what's insoluble, recall that you're required to know the following solubility rules. All salts that contain sodium, potassium, ammonium, or nitrate are considered soluble in water. That means any compounds containing those ions will be soluble. You can assume that any other compound is insoluble unless you're given additional information. So let's consider this reaction here between KCl and AgNO3. Recall that KCl, aqueous, dissociates completely, so it's actually a K plus and a Cl minus. AgNO3 also dissociates completely, again, using our solubility rules, potassium and nitrate. And that's going to give us insoluble AgCl. That's our solid, and dissociated KNO3. Again, K plus and NO3 minus always dissociate. Then recall we can take this complete ionic equation and turn it into a net ionic equation by canceling out our spectator ions. What we're left with then is the net ionic equation for this precipitation reaction, showing just the formation of the precipitate from its constituent ions. Here's a macroscopic look at a precipitation reaction. In this case, we have Ki in this beaker here, so K pluses and I minuses. Recall that dissociates completely. We have PbNO3 in this beaker, which essentially means we have Pb2 plus and NO3 minus ions. When you pour one into the other, the lead and iodine ions are going to find each other and form an insoluble product, PbI2. That's our precipitate. It sinks to the bottom as a solid. The other spectator ions remain in solution. The next type of reaction is an acid-base reaction. An acid-base reaction is defined as a reaction where one or more proton is transferred between chemical species. Just as a quick aside, if you take a hydrogen atom represented here, that contains a proton and a single electron. If we remove that electron to form an H plus ion, essentially we're just left with a single proton. So when we say proton in this context, that's the same as saying an H plus ion. So now let's look at a schematic. Here's our H plus ion, or our proton. In this case, it's bonded to some negative ion or anion, represented by A here. In this acid-base reaction, the H plus ion is going to transfer to our base here, and it's going to combine to give us this compound here, leaving behind the A minus anion that had been connected to the H plus, or the proton. So again, we see a transfer of a proton from one species to another. Here's some more examples of that same concept. Consider HCl and water. When HCl combines with water, the H plus, or the proton from HCl, will transfer and combine with the H2O to give us H3O plus and Cl minus. Representing this here in a diagram, here's our H plus, or our proton. It's going to transfer over to our H2O to give us H3O plus. Another example would be here water is combining with ammonia. In this case, water is going to transfer its proton. It's going to act as the acid. So one of those two H plus ions, or protons from water, will come over and combine with NH3 to give us NH4 plus, leaving behind the OH minus from the water. Looking at this as a particle diagram, let's take our H plus here, transfer it over to our NH3 to give us NH4 plus, leaving behind the OH minus. Finally, oxidation-reduction reactions. An oxidation-reduction reaction is a reaction where one or more electrons is transferred between chemical species. So juxtapose that to acid-base reactions where a proton is transferred. Here an electron is transferred. This will result in a change in the oxidation state of the atoms. We'll look more deeply at what is meant by oxidation states, But one easy way to think about it is it's kind of like the charge of each atom in a compound. They're not exactly the same thing, but we'll unpack that difference later. Oxidation-reduction reactions are typically abbreviated as redox reactions. Let's consider this example here. Here we have a neutral zinc atom and a +2 copper ion. In this reaction, we see that the zinc atom has become a charged zinc ion and the copper ion has become a neutral atom. That means electrons must have been transferred. In this case, 2 electrons were transferred from zinc to copper because zinc became Zn2+ and copper went from being 2+ to being neutral. Consider this example here where we have neutral zinc, which has a charge of 0, and Cu2+, which obviously has a charge of +2. When this reaction proceeds, it yields neutral copper and zinc with a +2 charge. This tells us that 2 electrons were transferred from zinc to copper, since zinc went from having a charge of 0 to having a charge of 2+, and copper went from having a charge of 2+ to having a charge of 0. Here's another example to consider. In this case, sodium and chloride both start as neutral elements. However, as you know, in the NaCl compound, sodium has a +1 charge and chloride has a 1- charge. That means that an electron was transferred from sodium to chloride to give us Na+ and Cl-. A common type of oxidation-reduction reaction is a combustion reaction. Recall that combustion reactions are when we have a hydrocarbon, or a compound containing carbon and hydrogen, combining with oxygen to form CO2 and water as products. We haven't yet learned how to identify oxidation states of each atom in a reaction like this. We will in a future video, but for our purposes, I'm going to go ahead and identify them for you. In this case, hydrogen has a +1 oxidation state, carbon is -4, oxygen is 0 since it's elemental. On the product side, oxygen has become -2, carbon +4, hydrogen remains +1, and oxygen -2. Don't worry about where these numbers came from just yet. Again, we'll unpack that later. But what I want you to notice is that carbon has gone from an oxidation state of -4 to +4, meaning it's lost electrons. And oxygen has gone from an oxidation state of 0 to -2, meaning it's gained electrons. Here's a list of a bunch of different reactions. Pause the video here and identify each as either acid-base, precipitation, or redox. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. The first and third reactions are precipitation. Notice we have aqueous reactants resulting in a solid product, or a precipitate. 2 and 7 are acid-base reactions because our proton or our H+ ion is being transferred in each case. In number 2 from HNO3 to H2O, and in number 7 from H2O to S2-. And finally, 4, 5, and 6 are all redox reactions. In this case, magnesium has gone from a charge of 0 to a charge of +2, oxygen from 0 to -2. So we can see that electrons were transferred and oxidation states or charges changed. Likewise, copper went from 0 to +2, silver +1 to 0. And number 6, while it's hard to identify oxidation states at this point, you should recognize that as a combustion reaction, which is a type of redox reaction. That brings us to the end of this video. Let's review our goals. First, we learned to define 3 types of reactions: acid-base, in which one or more proton, or H+, is transferred; precipitation, in which a solid product is formed from aqueous reactants; and redox, or oxidation reduction, in which one or more electron is transferred. Then we looked at how to classify reactions as one of those 3 types.